Welcome back to Statistics, Chapter 8.1, Estimating Mu when the Population Standard Deviation is Known. This is Monika Wahi, your Library College lecturer, bringing you more statistics. So let me just cut to the chase. What this lecture is about is confidence intervals, okay? So we're going to be talking about confidence intervals. Let's just be honest here. So at the end of this lecture, you should be able to state the formula for the margin of error. You should be able to explain how to choose Z sub C, that's how you pronounce that, Z sub C, when making a confidence interval. You should be able to state one of the assumptions behind X that needs to be met in order to make confidence intervals. You should be able to interpret what a confidence interval means. And finally, you should be able to demonstrate how to calculate sample size. So here's what we're going to talk about. First, I'm going to review a few key points from Chapter 7. Now, I know you're kind of sick of Chapter 7, but I'm just going to pull out a few key points that I want you to think about during Chapter 8 because I think it'll help you understand Chapter 8. Next, I'm going to explain what confidence intervals actually are. We're going to go through quite a bit of theory so you understand what we're doing when we're making a confidence interval. Next, I'm going to demonstrate how to calculate confidence intervals, and then I'm going to demonstrate how to calculate n, or sample size, if you want to know how big your sample should be for a certain confidence interval. So the first one of how to make confidence intervals, that's after you've already had your sample and measured it. The second one, demonstration of how to calculate sample size, that's before you get your sample if you want to know how many you need. Alright, so here's Chapter 7. Please humor me. I'm just going to pick out a few ideas that I want you to think about. So first of all, remember from back the slides I showed you, there were all these different types of inferences, and one of them called estimation. I said we're going to practice this in Chapter 8. Well, I wasn't lying. Here we are. So what's estimation? Estimation is where we estimate the value of a population parameter using a sample. Sounds like a logical thing to do in statistics. In this situation with the confidence intervals, what we're doing, we're trying to estimate mu from using a sample. Because mu is obviously a population parameter, and if you just have a sample, you don't know what mu is, but we try to estimate it from our sample. And so that's what Chapter 8 is really about. Okay, next, remember 7.1, right? Remember the empirical rule? And remember how I asked you all these questions about the probability of selecting an X above or below a cut point, or the percentage of data between a certain group. There was one question, though, I want you to think about, and that was this question about the middle 68%. So the question was, what are the cut points for the middle 68% of the data? And that literally meant that it had to be 34% on one side of mu and 34% on the other side of mu. And when I said, well, what are the cut points? What are the X's that mark that on this particular distribution? And it was 51 was the lower limit and 80 was the upper limit. So I just want to point out here that this means that the probability of selecting an X between 51 and 80 with this particular distribution was 68%. So technically, that's kind of like you would say, if I select an X from this distribution, I am 68% confident it'll be between 51 and 80. That's another way of saying this, okay? Okay, now we're going to skip ahead to Chapter 7.2 and 7.3. Now remember what we did there. We had already learned about the empirical rule. Now we figured out how to calculate X's for Z's that were in between the cut points of the empirical rule. So most questions focus on the probability of selecting X below or above a cut point that wasn't on the cut points of the empirical rule. So that was most of what you were doing in 7.2 and 7.3. However, there was one question I gave you on the slides about a middle 20%, so I'm bringing that one up. So this was the question. It's what scores mark the middle 20% of the data, right? So it'd be like 10% on one side and 10% on the other. And so what we did was we looked up what the probabilities were and what the Z's were, and we got the middle 20% of the data. And so the middle 20% of the data was 61.9 through 69.1. So I just wanted you to notice that that also could be said this way. It's like the probability of me selecting an X between 61.9 and 69.1 was 20%. Or I could say it this way. If I'm 20% confident that if I select an X from this distribution, it will be between 61.9 and 69.1. So if you've ever wondered how you can feel a certain percent confident, that's how you do it, is you just say it that way. You take a middle thing like this and you say the probability of doing this, you look at the probability and you say, I'm that confident, that percent confident that the X I select will be between these two cut points. And then I want to remind you what we did after that is we went into chapter 7.4 and 7.5. And this time we weren't just picking one X. We weren't looking at the probability of picking one X. We were looking at the probability of picking a sample or a set of X's that gave us an X bar that was between certain cut points, right? So this one was, what is the probability of me selecting a sample of 36 students with an X bar between 60 and 65? That was the way I was doing this question. So, again, we answered the question, right? The probability of selecting a sample of 36 so that the X bar is between 60 and 65 is 41%, which is another way of saying I am 41% confident that if I take a sample of 36 people from this class, their X bar will be between 60 and 65. So that's how you feel 41% confident. Because that's what I always had trouble with in statistics. I'm like, I don't know how to feel that way. Well, this is how you feel that way. But I wanted to point out this is not like the perfect example, because what we're going to be doing with confidence intervals is going to be centered around mu, which is a 0. This is lopsided. This is centered somewhere else because this was a different lecture, right? But what we're talking about is, what if you wanted to find the X bar lower and upper limits for the middle 90%, or the middle 95%, or the middle 99%? That's what you would be saying, is that, okay, well, between this lower limit and this upper limit, I'm 90% confident that the mu is going to be in there. That's what you're trying to do with the confidence intervals. Remember the central limit theorem? The confidence intervals work with the central limit theorem. And so, I'm sorry, more theory. So remember how we had that neighborhood of people, and we were taking samples of 5 of them and measuring their BMI, and we were trying to figure out what would we get if we got the X bars from every possible sample of 5 from that group, right? And of course we got millions, literally, of X bars, okay? And then we made a histogram of all those possible X bars, because each sample of 5 represented a sample we could have gotten if we'd just done one study. So in real life, we usually only get one sample. So if we get to look at all the different samples we could have gotten, we wonder, well, which one are we going to get? Where is our X bar going to be in our sample that we pick? Because we're only going to pick one. And mostly we're upset because we're not sure how far it's going to be from mu. So if you look at this histogram, there's a bunch of samples where the BMI, the mean BMI in the sample, the X bar, was less than 20. And there's also a bunch where it was more than 40. And that's probably not very representative, because you see where most of the X bars are between 25 and 30, right? And so we get worried if we think about, what if we get a sample that's on one of those tails? What do we do about that? So as you can see, just from 3 different samples, you have wildly different X bars. So I could have gotten one of these. So how do I know, right? Like, I feel uncomfortable because I know that that X bar might not be close to the mu. Well, the first thing you need to know is, don't get too excited about the X bar. Remember sampling error, how you're going to get an X bar and it's probably not going to be mu? Well, we know that, and we can handle it in statistics. In fact, that's how we handle it. It's with confidence intervals. What we just say is, okay, X bar is there, but we want to create a range or an interval around X bar with a lower limit and an upper limit, and then just say, okay, fine, we know X bar isn't right, but within this range, most of the X bars I could have gotten, like if I'd gotten other samples, most of their X bars would have fallen between this lower limit and this upper limit in this interval. But you can't actually say all. And I'll tell you why you can't say all. Is because if you came to me and you asked me what your grade was going to be, If I said, well, I can 100% assure you it'll be something between A and F, that's totally useless, right? And so if you said, well, I want to be 100% certain that between this lower limit and this upper limit, I've got my BMI, I say, okay, great. We'll make the lower limit 0, which nobody can have, and the upper limit 100, which nobody can have. There. Now I'm 100% confidence in there. So that's why you don't want all. You want a probability. You want to know if like 90% or 95% are in there. Because otherwise, the 100%, you could just take two huge numbers, one hugely low and one hugely high, and say they're all in there, and that just doesn't get you anywhere. So what I did was I superimposed the z distribution, the normal distribution, on top of that histogram of the x bars. And I just drew a lines for where the middle 95% would be, because I just know that. It's between negative 1.96 and positive 1.96. Okay? And so that's technically, if you wanted your 95% confidence interval, you'd have to find the x at negative 1.96 and the x at 1.96. And then that would be your lower limit and your upper limit of the middle 95% of the x bars. And so you'd say, okay, I'm 95% confident that the mu is somewhere in there because most of the x bars are in there. So I'm going to keep going with this example. So imagine you just took 100 samples of any size from this population, right? So maybe I'll take 100 samples of like 5. We can stick with 5. You get 100 x bars, okay, which is not what we normally do, but I just want to give you this example. You get 100 x bars, right? If you figured out the upper and lower limits for the middle 95% of the sampling distribution, you'll find that 95 out of 100 of your x bars were actually between those limits. And how I know this really works is that I use Excel and I can make up people. So I can make up a population of people with BMIs, all different sizes. Then I can take 100 samples of 5 from each of those fake people I made up in Excel, and then I can take the x bars and I can actually see this. This really works really well. That's why people are so convinced of it. But of course, you got to realize that there are 5 that don't fall in there. So in real life, when you're doing a study, you always ask yourself, am I getting one of the weird ones that fell outside or not? But you try to be 95% confident, if you're using a 95% confidence interval, that you're getting one of the ones in the middle. So if I was picking on 95% because I memorized this 1.96. So if you want the middle 95%, the z is always the same. It's always 1.96 on either side of mu, right? Negative 1.96, positive 1.96. It's just always the same, right? You just have to look it up. So people like me memorize that one. Like 95% is totally the most popular one in healthcare. Everybody uses 95. In the olden days, we used to use 99% more than we do now. But 95% has always been popular. These other ones aren't really that popular, but I just showed them to you for demonstration purposes. I want to pull out some points about vocabulary. So you're going to hear me say these 3 things. You're going to hear me say critical value z, and also z sub c, which is written like the z with a little c under it. Now, I remember when my professor first said z sub c, I had no idea what he was saying. I thought he was saying z sub c. So I was like, what is z sub c? Z sub c? Well, it's z sub c. And you'll see that sometimes, like whenever you have a letter, a little letter, and it's a little below, it's sub, right? So in it, and then also critical value z is also z sub c. So if you look at the table, you'll see that level of confidence is, we use c to stand for that. So if I'm like, I want the level of confidence of 95%, I could say c equals 95%, right? But if I do that, I'm forcing z sub c to be 1.96. They go together. So if I pick a c of 80%, then my z sub c, or my critical value c, is 1.28. And you know what it means by critical value, like it's critical. That's the cut point where you're going outside the confidence interval, so it's critical. That's why they call it critical value Z. So the Z you pick, or even the C you pick, determines the width of the interval around X bar. So you see, remember where 1.96 was? Well, that's for 95%. If you pick 99%, you'd be talking 2.58. Remember, like 3 is kind of big. That's kind of out there in Z land, right? Like that's close to the edge. So that's what happens is you get this wider confidence interval. And remember, you're going to get a grade in somewhere between A through F. Well, the wider it is, the less useful it is because the less precise it is. You don't really know exactly where it is. But in any case, whatever confidence level you pick, at the end, the generic thing you're getting ready to say is, I'm using the example 95%. I'm 95% confident the mu is between the lower limit and the upper limit. But you never actually say that. You have to interpret it with the thing you did. Like if I was doing blood pressure, I could say I'm 95% confident the population mean blood pressure, SBP, is between whatever my confidence interval was like 110 mmHg and 120 mmHg. So that's how you would actually say it. And don't worry about it. I will give you a demonstration. So just to remind you, I kind of am going over this theory in different ways so it sinks in. A confidence interval for mu is an interval that we've computed from sample data where the level of confidence, or the C, this percent, refers to the probability of having the resulting interval contain actually the value of mu. So when I say I'm 95% confident, I'm 95% confident this interval has mu in it. Another way of saying it is the level of confidence is the proportion of confidence intervals calculated from a random sample size of n samples that actually contain mu. So remember when I said, let's say I took 100 samples, if I had a 95% confidence interval, I would expect that 95 out of 100 or 95% of those intervals would have mu in it. So again, don't get too excited about X bar when you get it. Don't go, oh my gosh, it's high or low. Just remember, it's a point estimate, meaning a one-time estimate of a population parameter. There can be others. Like if you'd gotten a different sample, you'd have gotten a different X bar. Okay, so just don't get too excited about it. Because remember sampling error, right? Your X bar is not going to probably be your mu. So when using X bar as a point estimate for mu, you have to deal with the concept of the margin of error. Some books abbreviate it ME, but the one we're using uses just a capital E. And that's the absolute difference, meaning like it doesn't matter plus or minus, the absolute difference between the X bar you got and the mu. So I'm just going to give you an example of what I mean by E. So if we had gotten the X bar of 60 from these students and we magically knew mu was 65.5, our margin of error, our E, would have been 5.5 because that was different. If our X bar had been 90, and then our mu was really 65.5, then our margin of error is 24.5 because that's a difference between 90 and 65.5. And again, it's absolute difference, so you always make it plus. I just wanted to remind you what the word margin means. See, when you type like a report and you have margins, like you're supposed to have a margin of, 1 inch or whatever, it means a little space. And that's what you're doing, is you're making a little space of error, meaning somewhere in this space is where your mu is. So that's why it's called a margin of error. All right, now you can't just go around making confidence intervals without thinking about it. So first, I just want to go over the assumptions about X that you have to consider before making confidence intervals. X being the thing that you're measuring, that you're making your distribution out of, right? So first, X is out there in the world and you're drawing a simple random sample of size n from a population of X's. Notice this is a simple random sample. This is not a biased sample. Remember how, like, if you get a convenience sample, it's probably pretty biased? You can't do the confidence interval thing if you're getting a biased sample. So you're trying to get a simple random sample of a particular size from a population of X values that are hopefully normally distributed. Because as you can see under 3, if X itself has a normal distribution, then we know that X bar will have a normal distribution no matter how big our sample is. So we like it if we're drawing from a population of X values that has normal distribution. Oh, and also 2 says we have to know the value of the population standard deviation. So if we're doing that, and especially if we meet 3, that the X itself has a normal distribution, we're really excited about making our confidence interval because we know it'll work really well. But if we're in the situation where you see 4, we aren't sure about X's distribution. Remember, we only have a sample. We don't have like a lot of data from the population to even figure that out. So if we're not sure, we should get a sample of at least 30. But as you can see by 5, if it's definitely not normal, like it's skewed, like remember how we looked at some parameters from hospitals, right, that are totally skewed. So if I was sampling those hospitals, I'd be shooting for a higher sample size, like 50 or 100, because we're taking a simple random sample of size n, and n's got to be pretty big if you've got skewed data and you want to make a confidence interval. So basically what you're thinking about is your X, and if you got a simple random sample, if you have a population standard deviation lying around you can use, and then if X itself has a normal distribution, you don't need to worry about your sample size. If you're not sure, you want at least 30, and if you definitely know it's not normal, you want a large amount. Now, for a confidence level C, the critical value Z sub C is the Z-score such that the area under the curve is between negative Z sub C and positive Z sub C. And if you're like, you're just repeating yourself, I am kind of repeating myself, but I'm doing it in different ways because I know this is really difficult concept, and so sometimes people need to hear it differently. But this is one way of saying it, okay? Now I'm going to go on to talk about how to calculate a confidence interval. And trust me, it has something to do with all this theory. So here are the simple steps, right? So the step 1 is you make sure you have your X bar, right? Because you took a sample. You better have an X bar. And of course you're going to have an N because you took a sample and you know how many people you measured. But then you also need to make sure you have your standard deviation for your population lying around because you need those ingredients for this. Next, you have to pick C. And then that connects to whatever Z sub C you pick. So you see the table on the right, you have to select your C in the Z sub C that comes with it. So you're going to be given your X bar, your population standard deviation, and your N, and then you got to get picky about C and Z sub C. But once you've made those decisions, you calculate E, or the margin of error, using this formula. So see that there, beautiful formula, right? Then once you get that E, that margin of error, you have to get the lower and upper limits for your interval. So to get the lower limit, you subtract E from your X bar, right? So that's going to make X bar forced to be in the middle, because 5 is you add E to your X bar to get the upper limit. So I'm going to just walk you through these steps with an example, but that's all you have to do. It's almost like the theory was harder than actually doing it. I did want to do a shout out to this because the first time I learned this stuff, I could not get over this. I was like, okay, I get we're trying to estimate mu from a sample. But if we have a population standard deviation, why don't we have the population mean? Like, we obviously had to measure everybody to get the population standard deviation. Why didn't we just look at the mean at the same time? Like, why are we even doing this? So that was like a really difficult conceptual problem I had. But then I worked for a very short time at the Department of Public Health at the state of Massachusetts. And what I realized was when you're doing like population level health, the mu can and often should change. But the variation, which is measured by the standard deviation, tends to stay the same. So imagine that we studied at the Department of Health or Public Health a community where the blood pressure, the mu blood pressure, was just way too high. We'd study it, we'd find this really high mu, and we'd also find the population standard deviation of blood pressure. Then let's say we did work to try and lower the mu blood pressure, and we wanted to see what it was like a few years later after we did all that work. Well, we can't measure the whole population again. We'll just take a sample of them, But we can use the old population standard deviation because that generally doesn't really change that much. It's just the mu that's going to change. So that's like this huge explanation because I had this huge conceptual problem with this, and hopefully that'll solve your problem if you have this problem. And if you didn't have this problem, you probably just sleep better at night than I do. And just to illustrate this, this slide was available online, so I took it. It's just an example of one of the findings from this article on total knee arthroplasty, which sounds perfectly painful. But in any case, as you can see, this is BMI, since we're on the subject. Their BMI, their mean BMI changed as time went on, it went up. However, I can't demonstrate this to you, but in the paper you'll see that they had a standard deviation, and that standard deviation really didn't change much. So if let's pretend you measured everybody, the population in 2003 on the slide, we're just pretending. Then you wanted to see what was going on in 2007. You could use the old population standard deviation from 2003 and just apply it to 2007. But as you can see, even if you took a sample of those people in 2007, you probably get like kind of a higher X bar because there's a higher mu. All right. Another thing I want to get into before I actually demonstrate this is that for you standard error fans, you might have noticed that in the margin of error calculation, the standard error is hiding. So remember I taught you how to prep cook your standard error because you can use it a lot and then you don't have to deal with thinking about square root of n being underneath something. So the formula actually for the margin of error could technically be written like this. So if you're doing a quiz or something, you want to keep track of your SCE, your standard error, and reuse it if questions are asked about different levels of confidence, because only your Z sub C would be changing then. Your SE would be the same. So this is just a shout out to standard error fans. Okay, now I'm going to walk you through actually calculating a confidence interval when the population standard deviation is known, to give you an example. So here's our example. So remember the class of students that I was in, that I was telling you about, where we had such a hard test that nobody got 100%. So in that class of students, we studied the population standard deviation and we found it was 14.5, right? But now it's a new term, right? Same college, new term. And we have a new class of students, so we want to know if their mu is different. Like maybe the teacher got a little better, and so maybe their mu is a little higher. Who knows? Okay, so step one is make sure you have your X bar, your population standard deviation, and your N available. So we're going to take a sample of 100, just because it's easier that way. And I'm going to say we got an X bar of 63, right? That's not a very good score on a 100-point test, but it's a hard test, right? And we have our old population standard deviation to use. So we've done step one. Okay, so we have our X bar, our population standard deviation, and our N. Now let's do step two, where we have to pick C, which is the confidence level, and that forces you to use the Z sub C at that confidence level. So just as a demonstration, I'm going to pick 99% for C. So the Z sub C is 2.58. But I could have picked some other one. I just picked 99% because I felt like it. All right. Step three is to calculate the margin of error, or E. So remember our formulas up there. But then and standard error fans, there's a standard error in there. So I just first put up the numbers we need. Their X bar is 63, remember. Population standard deviation is 14.5. Our N is 100. Our C, our confidence level, is 99%, so our Z sub C is 2.58. So we just plug it into the equation, and we get the E is 3.7. Okay, so that's step three. We got E, which is 3.7. Now step four, you want to get the lower limit of the confidence interval. You subtract E from X bar. So our X bar was 63, and we got our new E, look, I put it in red, of 3.7, and then we subtracted, we get 59.3. So that's our lower limit. And see, I put that on the slide now. Now step five, you add the E, which is 3.7, to the X bar, which is 63, and you get 66.7. So you get your upper limit. And then what do you say? You say I am 99% confident the mu of the new class of students is between 59.3, which is the lower limit, and 66.7, which is the upper limit. And if we just think logically about that, that's about like 59 to 66. So if I was talking to you about your class and you're like, oh my gosh, it was so bad, the mean was 63, and you also tell me that the 99% confidence interval is 59 to almost 67, it really tells me everybody did pretty bad in that class. Like if 99% of the samples you could have taken would have gotten an X bar in between those two numbers, people are not doing well in that class. All right, so I just gave you one demonstration of how to calculate confidence intervals because it's actually a lot simpler than the other stuff we were doing. Like you just plug in the numbers and you do that and you do the interpretation. It's pretty easy. But sometimes you don't want to know you're not trying to estimate mu. In other cases, you're actually trying to figure out how many people to have in your study in order to estimate mu. So I'm going to show you how to do that if that's your problem. So I started by just putting up the steps to calculate sample size when the population standard deviation is known. So I just want you to look at the formula. It's actually the same formula, just rearranged so it's solved for n, right? Remember that square root of n, which is underneath the standard error? Well, how that gets dealt with is, you see on the right side of the equation, you have to square things, right? So basically, if you just look at that formula, you realize in order to calculate n, you need a z sub c, you need a population standard deviation, and you need an e. So here's how we're going to go about it. Step one is make sure you have your population standard deviation around and available because you're going to need it for this. Next, you have to make a decision. You have to pick C. So this is before you're doing your study. So you're saying, okay, how much confidence do I want when I'm done with my study, right? If you want 99% confidence, you're going to end up with more, needing more sample, right? Because then you'd end up putting that 2.58 in for z sub c up in that equation, because it's on the top, it'll inflate the number. If you don't need to be so confident, like if you look at 95%, you get a discount that's only 1.96. Then you don't need as much n. So it depends on how much money and effort you want to make. So so you have to pick C so you can get your z sub c, so you can put that in the formula. Then next you have to also pick how big of an E you want. So remember how big of a margin you want. If you pick a big margin, then you won't get a very precise estimate, right? Like you won't get upper and lower limits that are kind of close together so you can kind of know where it is, right? So you've got to also make a political decision of how big of an E you want. And then finally you plug all that into the formula and you calculate the sample size, or the n. So I'm coming up with a new question. How many students do I need if I want a 95% interval and I want my E to be 5? That's the way I start the question, okay? How many students do I need if I want this and that? Well, what does that literally mean? Let's just make a list here. First of all, we're going to use our population standard deviation, so I threw that in there, right? And then because I wanted a 95% confidence interval, our C is 95%, and then we're stuck with our Z sub C, which is 1.96, like I was showing you on the last table we were looking at. And I decided I wanted my E to be 5, so I put that in there. So that's steps 1, 2, and 3. So step 4 is calculate, so let's calculate. Alright, so what did we do? We plugged it into the equation. So we have Z sub C, which is 1.96, times the population standard deviation. We have the product of that divided by our E, which is 5. And then we take that whole thing to the second, and we get 32.5. So that's our n, right? But you need to like always round up due to it not being able to have like 0.3 of a person. So sometimes people ask me, well, do you round down because it's under 0.5? And I'm like, no, because you need at least 32.3 people and you can have zero point 0.3 of a person, so you always have to round up. So if you get a little piece of a person, you have to take the whole person. It's just the way people work. So that therefore your answer is actually 33. So if you wanted a 95% confidence interval and your population standard deviation was 14.5 and you wanted your margin of error to be 5, you would need to get a sample size of 33 people. So we finally made it to the end of this lecture. In conclusion, I started by reviewing some slides from chapter 7. I know you're kind of done with that, but I reviewed them because they related to the subject of confidence intervals. Next, I explained Z sub C and the level of confidence and the whole concept of the point estimate of X bar. Then I finally went into some application, right? Enough of the theory. Let's actually construct a confidence interval when the population standard deviation is known. And then, so I did one of those for you. And then we did an example of how to calculate sample size in case you are getting ready to do a study and you need to figure out how many people you need in it based on the population standard deviation you have and your choices of confidence level and of the size of E. And so if you thought you were 95% confident or 99% confident, here is someone who is 100% confident. That is a very confident peacock on that slide. Hello everybody. Guess what? It's time for statistics again. Chapter 8.2, Estimating Mu when the population standard deviation is unknown. It's Monika Wahi, your library college lecturer, here to talk to you more about confidence intervals. Now, at the end of this lecture, you should be able to state one way in which the Z distribution is like the T distribution and one way in which they are different. You should also be able to demonstrate how to find T sub C in the T table. You should be able to state how to calculate degrees of freedom, and you should also be able to explain how to calculate a confidence interval when the population standard deviation is not known. Alright, so here's what we're going to go through. First, I'm going to describe to you how and why the T distribution was invented and give you really the important backstory on why this came about. Then I'm going to show you how to use the T table when calculating confidence intervals when the population standard deviation is unknown. Now if you see there, that's a T table, but that's not the kind of T table we're going to use. However, this T table is probably better than our T table because it looks really yummy, doesn't it? Okay, the reason I'm using a very serious tone of voice is because this is a serious issue. What happens if you can't use the Z table? So I'm going to tell you about student's dilemma. Now, student wasn't really a student, okay? That's just a nickname for a guy who was having a political issue, so he couldn't use his real name, right? So I'll get to that in a moment. But first, I just want to go and set the stage for this political issue. Remember back in the last lecture, when you know the population standard deviation, you also have to consider some assumptions about X before you make your confidence intervals, okay? And these are the ones up here. You know, this was from the last lecture, but I want to call your attention to two things. One is obviously you have to know the population standard deviation. That's one of the things you have to really have before you use that Z table. Also, if you're not sure of X's distribution, you really should get a sample of at least 30. And if you know it's not distributed normally, like it's skewed, you really need a lot more. But you need at least 30. Well, those two requirements can limit you a lot, right? Because what if it's unknown? What if the population standard deviation is unknown? Like, for instance, let's say you're studying a new topic. Like now we have e-cigarettes. They're kind of new. Maybe we don't know population standard deviations about e-cigarettes. Or maybe we're starting to study a particular subgroup of people that we didn't really understand. Like we're doing more studies on transgender people right now. Okay, maybe we don't have a population standard deviation for the subgroup now because we're starting to do better studies. You know, that can be an issue. And also, what if you just plain old have small sample? What if you just can't get a lot of people in your study? Well, there are ways to work around it. So first of all, if you don't have a population standard deviation, you need to use some sort of estimate for that. And you can use a kind of lower quality estimate by using your sample standard deviation, right? I mean, their sample standard deviation is only going to be made out of however's in your sample. So it's not the greatest estimate of the population standard deviation, but it'll do. You could use that. But it also means if you're going to use your sample standard deviation that we kind of violate the whole central limit theorem, right? I mean, we need a super large sample or else we're violating the central limit theorem. So this is kind of what the problem looks like. And so here is that guy I was talking about that he had to hide behind his nickname, which was student. Okay, so in 1908, William Seeley Gossett had this problem. That's him on the slide. He worked at Guinness, the beer maker. And they use barley, I guess, to make the beer. And he needed to test samples of barley where he did not know the population standard deviation. And he also couldn't test large samples, so he had this problem. So this is actually a common problem. So what he did to solve the problem is he came up with his own distribution. I don't know why he called it the T distribution, but that's what he did. He called it the T distribution. But at Guinness, they had a rule at the time that everybody working there could not publish anything, no matter what. And he begged his boss, and his boss would not let him publish it. So he secretly published it, and they nicknamed him Student, probably because he was always doing calculations and stuff and acting like a student. So he published this new T distribution under his nickname Student, and now it's called the Student's T distribution. Although some people get really political about it and they say we have to call it Gossett's distribution. He was robbed of his whatever, but we can call it Students. I'm sure he's fine with that. He seemed like a really modest guy, actually. Um, okay, so let's talk about Student's T distribution. What I've got on the slide is actually the Z distribution, but I wanted you to kind of think about that so you could see what the differences are between the Z and the T distribution. So like the Z distribution, the T has its own table. So don't go to the Z table if you want to look up T. You got to go to the T table. And unlike Z, T is different depending on the size of n. So remember, it doesn't really matter how many n's you have, how big your n is, how many x's you have. You can go look up the Z table and it just doesn't matter. On the T table, you actually have to know this thing called degrees of freedom. And how you calculate the degrees of freedom is you go n minus 1. And so obviously you can't get the degrees of freedom unless you know what n is. And if you don't get the degrees of freedom calculated, then you don't know how to find what you need in the T table. So that's sort of the key to the T distribution that's different from the Z distribution. So like for example, if you have degrees of freedom of 3, the curve looks kind of like the Z distribution, but it's really shallower. And see how the tails are a little thicker like that? Now I'm going to show you an example of, okay, here's the degrees of freedom of 5. So if your n was 6 and it was degrees of freedom were 5. See how it gets stretched up more and the tails are not as thick? So as you increase your sample size, here let's look at 10. It keeps going up and eventually you're right, it's going to meet the Z. But that's why you need to know your degrees of freedom, because you're going to get a different number for T no matter or depending on which degrees of freedom you have. So I'm just going to review here these properties of the student's T distribution. So like Z, the T distribution is symmetrical around 0. Like you may have not noticed that from what I was just showing you. But yeah, that's similar. But unlike Z, the distribution depends on the degrees of freedom, which depends on the sample size, since the degrees of freedom is n minus 1. And like Z, the distribution is bell-shaped, but unlike Z, the tails are thicker, right? Like the thing gets kind of stretched out. And so as the degrees of freedom and the sample size increases, the T distribution approaches the Z distribution. Like you saw how that, as I increased the degrees of freedom, that curve kept going up until eventually it would meet the Z. And also for the T distribution, like the Z distribution, the total area under the T curve is always 1. So we're dealing with the same kind of area probability situation. All right, now that I've introduced you to the t-distribution, I'm going to explain to you how to find the confidence interval when the population standard deviation is unknown and you get a new formula. Okay, let's just go over what the slide says. Okay, these are the steps. And then I'll go through an example. So step one is make sure that you've calculated your x bar and your s, right? So you have a sample of n, size n, so you need to know n, and you need to calculate the x bar, which is pretty easy, but you need to calculate s, which is not that easy, right? Because remember that from chapter 3. So you got to get all that together and get that ready. So that's step one. Then step two is you got to select your confidence level, like C. And like I was just saying, depending on the confidence level and also the degrees of freedom, then you get that stuff together and you look up T sub C in the T table. And I'll demonstrate that, like how to do that. After you do that, then you have to calculate your margin of error. Only you have to use this formula because we don't have Z. You'll notice it looks a lot like the Z one, only instead of Z sub C, you have T sub C. And instead of population standard deviation, you have sample standard deviation because we don't have the population standard deviation. So we're going to use this estimate using the sample. So once you get your E, you're familiar with step 4 and step 5, right? Because step 4 is to get the lower limit, you subtract E from x bar, and step 5 to get the upper limit, you add E to x bar, the margin of error. And so I'm going to demonstrate this, and then I'll also be able to show you like how to deal with the T table. Okay, so hello, time for class, right? Only, we're in a different college. So the population standard deviation is unknown. See, we're studying a different subgroup. But we want to know their mu, and we're going to do our best. So first, let's obtain their x bar. And let's calculate their s, and let's count up the n. So I'm pretending at the new different college where we don't know the population standard deviation that they did their test and they got x bar of 68, which is a little bit better than we were doing before. And I made up that they got the sample standard deviation was 10, and that we studied 30 people, so n equals 30. So we did step 1. We pulled together our x bar, our s, and our n. Okay, now we need to decide on a c, right? So I just picked 90%. We also need to calculate our degrees of freedom. And so that was really hard, right? That's n minus 1, 29. That's probably the easiest thing you'll learn in this class is degrees of freedom. I just love that. At least something's easy. Okay, but now we're going to do something kind of hard. We're going to look that up. We're going to look up T sub C in the T table. So before we go to the T table, I just want you to remember we've selected 90% for the confidence level, and our degrees of freedom are 29 because we need those ingredients before we go to the T table and we go find our T sub C. Okay, here we are at the T table. Okay, so please notice that the T table is on page A10. That's Appendix 10. Also notice that it's only one page. Okay. Now I know this doesn't really look a lot like the Z table, but don't worry. I'll help you understand. First, we're going to look over here and notice this DF. This is degrees of freedom, right? And they're down this way. So remember the one I told you to remember we're looking up, which is 29? This is where we're going to look for the 29 is in here. Now you'll notice over here it says C for confidence level, and then you'll notice these two things under here. Ignore these two things right now, these two rows under here, and just pay attention to C. Because you know what C is. Basically, it's our confidence level, right? And remember I told you to remember 90% because that's the one we picked. As we go across here, sure enough, here's 90%, right? If you had done 95%, it'd be over here. Here's 99. But this is 90. Okay, so we looked up our C here, and now we're going to go under our DF, our degrees of freedom, and we're going to find the number there. So let's scroll down. So this is the fourth one over, right? So I got to remember that as we scroll down. Okay, here's 29. So the fourth one over is the one we want, which is 1.699. So as you can see, it matters what your degrees of freedom are, because like if we'd gotten, for instance, like 20, we had degrees of freedom of 20, we'd have like a bigger t, meaning that would make our e, our margin of error, bigger, and that would mean that our confidence interval got wider, and that's the penalty we pay for having smaller sample. But here up at 29, we get a little discount. We get it a little smaller, 1.699. And as you get up there, you'll see that this just keeps getting smaller and smaller. You'll also notice that they start kind of cheating over here. After 30, they jump to 35, 40, 45, 50, because it's hard to fit all of this on one table. You'll find different tables. Sometimes they'll go out. But one of the things I want you to notice is that down here it says like 120, and then it says infinity. And infinity, like over here, the 95%, 1.96, what's that? That's Z, right? So this is sort of the table version of what I showed you in a diagram. That if you get enough degrees of freedom, or sample size, n, then you end up just having Z. So this is really to solve the problem like student had, where you have small sample, and also it's compounded by the fact that you don't have a population standard deviation. So just to remind you, when you go to the t-table, look for C and choose your confidence level, and then go down and go find your degrees of freedom, which ours was 29, and here we go. And now hold that thought. Remember this number, 1.699. All right, we're back. We looked up T sub C. That was a lot of work. So here it is. T sub C, 1.699. Okay, we did step 2. Now we can move on to step 3 because we have all our ingredients. We're going to calculate the margin of error using this formula. So here we are calculating E. So we took our T sub C and we multiplied it by our standard error, which is 10 over the square root of 30, because 10 is our standard deviation and 30 was our n, and so that's how you make the standard error, right? So once we did that, we got 3.1 for our margin of error. Okay, great. And now it's all smooth sailing, right? We're used to 4 and 5, but let's just do it out here. So I added that margin of error to our list, so that's 3.1. So we subtracted 3.1 from our x bar, which was 68, and we added it to our x bar to get our lower and upper limits, 64.9 and 71.1. So this is what you say is, we wanted to know, we said class from a different college, what is their mu? And you say, I am 90% confident that the mu of the class from a different college is between 64.9 and 71.1. That's how you say it. So just to recap, if you know the population standard deviation, like in the last lecture, then you have a very robust measurement of variation, right? Because it's based on the whole population. This allows you to use the z-table, as long as your x is normal, or as long as you have a lot of sample, right? So if your x is normal, you don't need as much sample, but if it's not, or if it's iffy, you need a lot of sample. But if you have that population standard deviation, then that makes all the difference. And z-scores are smaller than t-scores, which means that your margin of error is always going to be smaller if you can use the z-table. So your confidence interval will always be smaller if you can use the z-table. So that means you have a more precise estimate of mu. So the smaller your confidence interval is, the more you kind of know where mu might be. And you like that. So using the z-table is great, and that's what's great about having a population standard deviation. But unfortunately, that's not always the case. Like with student, he had all these issues. And sometimes in healthcare, we have these issues because we can't get large samples of certain kinds of patients or certain populations. And also, sometimes we just don't know their population standard deviation. And there's not going to be any way we can figure it out. So if you don't know the population standard deviation, then you really just don't have a very good measurement of variation in your data. But as long as your x is normally distributed, you can use the sample standard deviation as a stand-in instead. And if you are lucky enough to have a sample size bigger than 100, you can use the z-table, or like above that 120, where it's infinity, because they're the same at high numbers. But if you have a sample size that's smaller than 100, you'd probably be safer using the t-table. And if it's smaller than 30, you definitely need to be using the t-table because it really matters at those low numbers. So in conclusion, students' t-table was really useful to us, and it was really useful to him and everybody else who needs to deal with smaller samples and when you don't have a population standard deviation. So you can actually make a confidence interval and you can actually estimate mu anyway, even with these problems. And then I concluded this lecture with a demonstration of how to calculate a confidence interval using the sample standard deviation and using the t-table. Now, I just want to point out something. This guy was at Guinness. Why didn't he name it a beer table?